Evening settled slowly over the southeastern coast of Australia. By the early 1960s, the corridor between Sydney and Melbourne had already become one of the busiest air routes in the southern hemisphere. Airliners moved steadily between the two cities, carrying businessmen, families, government officials, and tourists across a stretch of coastline and farmland that had long been the spine of Australian aviation. The flight time was short, just over an hour in favorable conditions. Routine, predictable. On most days, dozens of departures cross a route without incident. But aviation history has a way of revealing itself not through extraordinary flights, but through the ordinary ones. Flight 538 was expected to be one of those ordinary journeys. The aircraft sat quietly on the tarmac at Sydney Airport, its metal fuselage reflecting the fading amber light of early evening. Ground crews moved beneath the wings with practiced efficiency, checking panels, loading baggage, guiding passengers toward the boarding stairs. The aircraft itself represented the confidence of post-war aviation. Turboprop airliners had become the backbone of domestic travel across Australia. Faster than piston aircraft, smoother in flight, and capable of operating efficiently across medium-distance routes, they symbolize the industry's steady modernization. From the terminal windows, the aircraft looked calm and composed. Inside, the cockpit was already alive with quiet preparation. Switches clicked methodically across the overhead panel. Navigation instruments warmed to life, their needles slowly stabilizing. Gyroscopic indicators spun silently as electrical systems came online. In the left seat sat the captain. Years of flying experience had shaped a rhythm that required little conscious thought. Each pre-flight checklist flowed into the next with mechanical precision. The aircraft systems were examined in a sequence refined through thousands of hours in the air. Beside him, the first officer monitored the engine gauges as the ground crew prepared for startup. Temperatures, fuel flow, electrical load. Each parameter remained well within normal limits. Outside, the last passengers climbed the narrow boarding steps and disappeared into the cabin. Flight attendants guided them toward their seats as luggage compartments closed overhead with soft metallic clicks. Through the cockpit windows, the runway lights began to glow against the deepening dusk. Night flying had always carried a different atmosphere. The visual world outside the aircraft shrinks dramatically after sunset. Landmarks fade into shadow. Pilots rely more heavily on instruments, small mechanical indicators that quietly translate the invisible physics of flight into readable information. Altitude, attitude, heading, airspeed. Every motion of the aircraft becomes filtered through those instruments. For experienced crews, the transition is seamless. But when something begins to go wrong, night removes many of the cues that would otherwise reveal it. The engines started one at a time. Each turboprop engine spooled upward with a rising mechanical whine before settling into a steady hum. Propellers blurred into translucent discs as power stabilized. The cockpit vibrated lightly as the aircraft became a living machine. Taxi clearance arrived shortly afterward. The aircraft began rolling slowly toward the runway, its navigation lights blinking red and green against the growing darkness. Inside the cockpit, the workload increased slightly. Taxi checks, flight controls, trim settings. The captain moved the control column gently from side to side. The ailerons responded in unison, their movement visible along the wings. Everything appeared normal. Routine. At the runway threshold, the aircraft paused briefly. The final checks were completed in silence. Then the throttles advanced. The engine surged forward, propellers biting into the evening air. Acceleration pressed passengers gently back into their seats as the aircraft gathered speed along the runway. 90 knots. 100. The captain eased back on the control column. The aircraft lifted smoothly into the air, leaving the runway lights behind as the city of Sydney spread out beneath them. Climb power was set. The The landing gear retracted with a muted mechanical thud. Within minutes, the aircraft was climbing steadily into the darkening sky along the well-established route toward Melbourne. Below them, the coastline began to fade. Above them, the sky remained calm. At first, there was nothing unusual about the flight, but aviation accidents rarely begin with dramatic events. More often, they begin with something subtle, something small, something that appears insignificant in the moment. Inside the cockpit, one of the instruments shifted slightly. The movement was small enough that it could easily be dismissed as routine fluctuation, but experienced pilots noticed changes instinctively. The first officer looked briefly at the panel. Engine readings, fuel pressure, electrical load. Everything still appeared within normal operating ranges. The aircraft continued climbing. The cabin remained quiet. Passengers settled into their seats, some opening newspapers, others looking through the small oval windows at the darkening sky. From the outside, the aircraft remained stable, its navigation lights blinking steadily as it followed the invisible corridor between Australia's two largest cities. But inside the cockpit, the crew began to sense that something was not entirely normal. A slight vibration, barely perceptible. Then another. The captain adjusted the controls slightly, testing the aircraft's response. For a moment, the vibration faded. Then it returned, not strong, not violent, just enough to raise a question. In aviation, questions demand answers. The crew began scanning the instruments more carefully now. Propeller synchronization, engine temperatures, oil pressure, still within limits, still acceptable. Yet the vibration persisted. Aircraft systems in the early 1960s were sophisticated for their time, but they lacked many of the automatic warnings that modern pilots rely upon today. Pilots had to interpret symptoms themselves. Small changes, subtle sensations, mechanical feedback transmitted through the airframe. The aircraft continued climbing. Altitude increased steadily. The autopilot may have been engaged briefly to reduce workload, but the captain remained alert to the unusual vibration moving faintly through the controls. Outside the cockpit windows, darkness now surrounded the aircraft completely. The lights of coastal towns appeared far below as scattered clusters of yellow. Above them stretched an empty sky. Inside the cockpit, the vibration changed slightly. Not stronger, but different. The captain felt it through the control column. A rhythmic tremor. Mechanical, unpredictable. The crew exchanged a brief glance. Something within the aircraft was no longer behaving exactly as expected. Moments like this are often invisible in accident histories. There is no dramatic sound, no alarm, only the growing awareness that a system somewhere inside the aircraft is beginning to drift away from normal operation. The aircraft continued north along the airway. Air traffic controllers on the ground saw nothing unusual on their instruments. To them, Flight 538 remained just another routine departure, moving steadily along its assigned route. But inside the cockpit, attention had narrowed. The captain made another small control input. The aircraft responded, yet the vibration remained. It was subtle but persistent. Something mechanical was changing, and neither pilot yet knew why. Far below, the coastline of New South Wales slid slowly past in darkness. The flight had only just begun, but within the aircraft, the first quiet signals of a much larger problem had already appeared. Signals that would soon demand immediate decisions. Signals that would challenge both the crew and the aircraft itself. Signals that would eventually turn an ordinary evening flight into one of the most serious aviation accidents in Australian history. The investigation that followed would reveal a chain of events far more complex than anyone on board could have imagined in those early moments after departure. But for now, the aircraft continued forward into the night, engines steady, instruments glowing softly. And somewhere within the structure of the machine, an unseen failure was beginning to unfold. In the early 1960s, commercial aviation in Australia had entered a period of remarkable confidence. Less than 2 decades earlier, the country's domestic air network had still relied heavily on piston-engine aircraft operating across vast distances between isolated cities. But by the beginning of the 1960s, technological progress had reshaped the industry. Turboprop aircraft had arrived. Air travel was becoming faster, more reliable, and more accessible to the public. And nowhere was this transformation more visible than along the route connecting Sydney and Melbourne. The two cities formed the central axis of Australia's economic life. Government agencies, financial institutions, manufacturing companies, and media organizations all operated across both urban centers. Business travelers moved frequently between them, often making the same journey multiple times each month. Rail had once been the dominant link between the cities, requiring nearly an entire day of travel. Aircraft changed that calculation completely. By the early 1960s, passengers could depart Sydney Airport in the evening and arrive at Melbourne Airport little more than an hour later. The route quickly became one of the busiest domestic air corridors in the Southern Hemisphere. Airlines scheduled frequent departures throughout the day. Aircraft moved along the corridor in a steady rhythm. Most flights were uneventful. Australian domestic aviation at the time operated under what was known as a two airlines policy, a regulatory framework established by the federal government to maintain competition while preserving stability in the market. Under this arrangement, two major carriers shared the domestic trunk routes. Trans-Australia Airlines, a government-owned airline created in the aftermath of World War II, and Ansett Airways, a rapidly expanding private carrier that had grown from a regional operation into one of the country's dominant aviation companies. Both airlines operated nearly identical aircraft fleets in order to maintain balance under the regulatory system. Passengers often selected flights based simply on schedule. From a traveler's perspective, the experience between the two airlines felt nearly identical. Similar aircraft, similar routes, similar service. The aircraft at the center of Flight 538 belonged to a generation of turboprop airliners that represented a technological bridge between the piston engine era and the coming age of jet travel. One of the most widely used aircraft on Australian domestic routes during this period was the Vickers Viscount, first introduced in the late 1940s. The Viscount was among the world's first successful turboprop passenger aircraft. Its four Rolls-Royce engines drove large propellers capable of producing smooth, efficient thrust. Compared with earlier piston aircraft, the turboprop offered several advantages. The engines produced less vibration. Cabin noise levels were lower. Cruising speeds were significantly higher. Passengers noticed the difference immediately. Flying on a turboprop felt modern, refined, reliable. Large oval windows provided a wide view of the landscape below, while pressurized cabins allowed aircraft to cruise comfortably at higher altitudes. For many travelers, flights between Sydney and Melbourne became routine parts of professional life. But aviation in the early 1960s still existed in a transitional period. Aircraft technology was advancing rapidly, yet many safety systems common in modern aviation had not yet been developed or widely implemented. Cockpit instrumentation remained almost entirely mechanical. Navigation relied heavily on ground-based radio beacons. Weather radar was not always installed on domestic aircraft. Most importantly, many aircraft operating during this period did not yet carry modern flight data, recorders capable of preserving detailed information about system performance and crew actions. In the event of an accident, investigators often had to rely on physical wreckage, witness accounts, and maintenance records to reconstruct the final moments of a flight. The absence of recorded cockpit data could make investigations complex and sometimes inconclusive. The airspace between Sydney and Melbourne was well established by the early 1960s. Aircraft typically followed a defined airway along Australia's southeastern coastline, supported by a network of radio navigation beacons. Pilots monitored signals from ground transmitters that allowed them to track their position even in darkness or poor visibility. This system, though reliable, required constant attention from a flight crew. Navigation instruments needed to be interpreted carefully. Course corrections were made manually. Unlike modern satellite navigation systems, these radio-based methods provided only indirect positional information. Pilots had to translate signal strength and instrument indications into a mental picture of the aircraft's position relative to the route. Experienced crews handled this task easily, but added another layer of workload inside the cockpit. Weather along the southeastern Australian coast could vary significantly depending on the season. Moist maritime air frequently moved inland from the Tasman Sea, bringing layers of cloud and occasional turbulence across the region. Even on relatively calm evenings, temperature changes at different altitudes could produce pockets of unstable air for turboprop aircraft operating at moderate cruising altitudes. These atmospheric variations were usually manageable. Pilots simply adjusted altitude or course as needed. Still, weather remained a constant variable. Every flight required crews to monitor the atmosphere carefully as they climbed toward cruising altitude. Behind every commercial flight was an intricate network of operational planning. Airline dispatchers reviewed weather forecasts, route conditions, and aircraft performance before approving each departure. Maintenance crews inspected aircraft between flights, ensuring that engines, propellers, and flight controls met operational standards. Pilots reviewed fuel loads, weight calculations, and navigation procedures. The system was designed with multiple layers of oversight. Each layer served to reduce risk, and most of the time, the system worked exactly as intended. Yet aviation safety often depends not on the absence of problems, but on how systems respond when small problems begin to appear. Aircraft are complex machines. Thousands of individual components operate simultaneously during every flight. Engines spin at thousands of revolutions per minute. Hydraulic systems move control surfaces against the force of the wind. Electrical systems power navigation equipment and cockpit instruments. Even minor irregularities within one of these systems can create subtle changes in how an aircraft behaves. Pilots are trained to detect those changes quickly, but in some situations, the symptoms may emerge slowly, quietly, gradually building until they become impossible to ignore. By the time Flight 538 departed Sydney Airport, the broader aviation system surrounding it appeared stable and mature. The route was familiar. The aircraft type had accumulated thousands of flight hours across the global airline industry. Maintenance procedures followed established standards. Crew training reflected years of operational experience. From every outward perspective, the flight fit neatly into the routine flow of Australian domestic aviation. Passengers boarded expecting an ordinary journey. Ground crews prepared the aircraft as they had prepared countless others. Air traffic controllers monitored the skies with quiet efficiency. Nothing about the departure suggested that this flight would soon become the subject of intense investigation. Nothing suggested that aviation authorities, engineers, and investigators would eventually examine every aspect of the aircraft, the crew, and the operating environment in search of answers. Yet accidents rarely emerge from a single cause. They grow instead from a chain of conditions, technical, operational, and environmental, that gradually align. Understanding those conditions requires looking more closely at the aircraft itself, the crew responsible for flying it, the environment surrounding the flight, and the aviation systems that govern operations at the time. Only by examining each of these angles can the full picture begin to emerge. Aircraft, crew, environment systems. Understanding an aviation accident requires more than examining a single moment in time. Aircraft accidents rarely emerge from one isolated cause. Instead, They develop through an interaction of factors: mechanical design, operational procedures, human decision-making, and environmental conditions. Each factor alone may appear manageable, but when several begin to interact, the margins for safety can narrow quickly. To understand what happened to Flight 538, investigators would later examine four critical angles: the aircraft, the crew, the operating environment, and the aviation systems governing flight operations during the early 1960s. The aircraft, at the center of the investigation, stood the aircraft itself. The Vickers Viscount had earned a reputation as one of the most successful turboprop airliners ever produced. Developed in the United Kingdom during the late 1940s, the aircraft represented a major step forward in commercial aviation. It combined turboprop propulsion with pressurized passenger cabins and improved passenger comfort. By the early 1960s, Viscounts were operating across Europe, North America, and Australia. Airlines valued the aircraft for several reasons. Its four Rolls-Royce Dart turboprop engines provided reliable performance and efficient fuel consumption. The aircraft cruised comfortably at moderate altitudes and offered a smoother ride than earlier piston-engine airliners. Passengers often noticed the quietness of the cabin and the large oval windows that became one of the Viscount's most recognizable features. From an engineering perspective, the aircraft was considered robust, but like all aircraft designs, it carried certain structural characteristics that engineers monitored carefully over time. The Viscount's wings supported four powerful turboprop engines, each driving large propellers. These propellers generated both thrust and aerodynamic forces that interacted with the aircraft structure. Under normal circumstances, those forces remained well within design limits. However, if propeller systems became imbalanced or control surfaces began oscillating under certain aerodynamic conditions, vibrations could develop within the airframe. Such vibrations might be subtle at first, but if allowed to grow unchecked, they could place increasing stress on structural components. Aircraft manufacturers and airlines therefore relied heavily on routine maintenance inspections to detect any early signs of fatigue or imbalance within the aircraft systems. In most cases, these inspections prevented problems from developing further, but aviation history has occasionally shown that structural or mechanical issues can remain hidden until they emerge under very specific conditions during flight. The crew, aircraft technology alone cannot ensure safety. Human judgment remains a central part of every flight. The pilots responsible for Flight 538 represented the professional standards of their time. Airline pilots in the early 1960s were highly trained and experienced individuals who had often begun their careers flying piston aircraft before transitioning to turboprop airliners. This progression created pilots who were deeply familiar with the fundamentals of flight. Unlike modern aircraft with extensive automation, turboprop airliners of this era required constant manual oversight. Pilots actively managed engine settings, monitored mechanical gauges, and interpreted navigation signals from ground stations. Inside the cockpit, the workload was shared between the captain and the first officer. The captain held ultimate responsibility for the aircraft, navigation decisions, altitude adjustments, communication with air traffic control. All fell under the captain's authority. The first officer assisted by managing engine settings, monitoring instruments, and verifying navigation information. This cooperative system allowed the crew to maintain situational awareness, even during busy phases of flight. However, the cockpit technology of the early 1960s also meant that subtle mechanical changes might not trigger immediate alarms. Pilots relied heavily on physical sensations, changes in vibration, alterations in engine sound, small movements felt through the control column. These cues often provided the first indication that something unusual was developing within the aircraft. Detecting and interpreting those signals required experience and careful judgment. The environment. The flight path between Sydney and Melbourne crosses a varied stretch of southeastern Australia. From the air, the region appears calm and expansive. Coastal plains give way to farmland, forests, and occasional mountain ranges further inland. Most flights along this route follow established airways designed to guide aircraft safely between navigation beacons. During daylight hours, pilots often maintain visual awareness of the terrain below. At night, however, the environment becomes far less forgiving. Darkness removes visual references. The horizon disappears. Cloud layers can further obscure the ground. Under these conditions, pilots must rely almost entirely on cockpit instruments to maintain stable flight. Even minor instrument irregularities can therefore become more significant at night than during daylight operations. Weather also plays an important role in this region. Air flowing inland from the Tasman Sea frequently creates layers of cloud and occasional turbulence across southeastern Australia. While these conditions rarely threaten a properly functioning aircraft, they can introduce small disturbances in airflow around the wings and control surfaces. If an aircraft already carries a hidden mechanical vulnerability, such disturbances may amplify its effects. Investigators studying aviation accidents therefore consider environmental conditions carefully, even when weather appears relatively calm. The atmosphere is never perfectly still. Small forces constantly act upon the aircraft in flight. Aviation systems of the era. Beyond the aircraft and its crew lies a broader framework, the aviation system itself. In the early 1960s, commercial aviation safety procedures were evolving rapidly, but had not yet reached the technological sophistication seen today. Modern aircraft carry digital flight data, recorders capable of capturing thousands of parameters every second. Cockpit voice recorders preserve pilot conversations. Advanced warning systems detect dangerous flight attitudes or proximity to terrain. None of these systems were widely available on turboprop airliners at the time. Investigators studying accidents during this period faced significant limitations. Without detailed recorded data, determining the precise sequence of events required careful reconstruction from physical evidence. Wreckage distribution, engine damage patterns, control surface positions. These clues often form the backbone of accident investigations. Maintenance documentation also played a critical role. Airlines maintained detailed records of inspections, component replacements, and reported irregularities. Investigators examined these records to determine whether the aircraft had experienced any prior mechanical concerns that might relate to the accident. In addition, regulatory oversight from national aviation authorities attempted to ensure that aircraft fleets remained safe through regular inspection requirements and airworthiness directives. Yet aviation is an industry built on constant learning. Each accident reveals new insights, new procedures, new safety measures. Sometimes, those lessons emerge only after investigators have spent months, or even years, piecing together the chain of events. By the time Flight 538 departed Sydney Airport, all of these elements were already in motion. A proven aircraft design, an experienced flight crew, a familiar air route, a functioning aviation system that had supported thousands of successful flights. Individually, none of these factors suggested danger, but aviation accidents rarely originate from a single dramatic failure. More often, they emerge from convergence of small vulnerabilities, mechanical, environmental, and human, that gradually align in unexpected ways. Somewhere during the flight northward from Sydney, the first signs of such a convergence had already begun to appear. A faint vibration, a subtle irregularity. At first, these signals seemed minor, but within minutes, they would demand the full attention of the crew, and soon afterward, they would escalate into a situation no pilot ever expects to face. The accident As Flight 538 continued along the coastal airway north of Sydney, the subtle vibration first noticed in the cockpit had not disappeared. In aviation, vibrations are not unusual. Turboprop aircraft naturally produce a certain amount of mechanical feedback through the airframe as engines spin and propellers slice through the air. Pilots become accustomed to these sensations. They learn the normal character of the aircraft, how it feels, how it sounds, how it responds to small control inputs. What matters is not the presence of vibration itself. It is change, and change was beginning to make itself felt within the aircraft. At first, the vibration remained mild. It appeared intermittently, passing through the control column in a faint rhythmic tremor. The captain adjusted engine power slightly, a common step used to determine whether the sensation might be linked to a particular engine or propeller. Small power changes can sometimes shift the resonance frequency of a turboprop system, reducing the vibration. For a brief moment, the tremor seemed to ease. Then it returned again, still subtle, still manageable, but persistent. The crew now had a decision to make: continue monitoring the situation, or begin preparations to return toward Sydney. At this stage of the flight, the aircraft had only recently reached its cruising altitude. Returning would have been operationally straightforward. Yet pilots must constantly balance caution with practicality. Minor mechanical irregularities often resolve themselves after small adjustments. An immediate diversion is not always necessary. The crew continued to observe the aircraft carefully. Minutes passed. Then the character of the vibration changed. The tremor that had once been faint now became more noticeable. It moved through the aircraft structure with greater intensity, transmitting to the control column and rudder pedals. In turboprop aircraft, vibrations can originate from several sources: an engine imbalance, a propeller blade malfunction, or oscillations developing within the aircraft's aerodynamic surfaces. The captain reduced power on one engine slightly to test whether the vibration would diminish. The result was inconclusive. The vibration remained. Now it was becoming difficult to ignore. Inside the cockpit, attention narrowed. The first officer scanned the engine instruments again. Oil pressure, fuel flow, turbine temperature. All indications appeared normal. If an engine had suffered internal damage, the instruments would likely show signs of abnormal operation, but no such warnings appeared. This created a troubling situation. The aircraft was behaving abnormally, yet the instruments offered no clear explanation. Without a clear cause, diagnosing the problem became far more difficult. The vibration intensified further. What had once been a mild tremor now began to disturb the aircraft's stability. Passengers in the cabin may have begun to notice the motion as well, a faint shudder passing through the fuselage. At cruising speed, aerodynamic forces acting on the aircraft are significant. When structural vibrations develop, those forces can amplify the movement rapidly. A phenomenon known as aeroelastic flutter can occur when airflow over a control surface interacts with the structure supporting it. Under certain conditions, this interaction can produce oscillations that grow stronger with time. Aircraft designers work carefully to prevent such conditions from occurring. But if structural components become weakened or if aerodynamic forces interact unexpectedly with a component, flutter can begin suddenly. Once it begins, the situation can escalate very quickly. The crew likely attempted further power adjustments. Reducing airspeed is often one of the first responses to unexplained vibration, as lower speed reduces aerodynamic stress on the aircraft. But reducing speed also reduces the effectiveness of certain control surfaces. Balancing these factors requires careful judgment. Inside the cockpit, the captain maintained firm control of the aircraft. Yet the vibration continued growing stronger. The aircraft began to feel increasingly unstable. The control forces changed. Pilots describe such moments as the aircraft talking through the controls. The control column may begin to shake. The rudder pedals may tremble. These signals indicate that forces within the aircraft structure are no longer behaving normally. The vibration now had a distinct rhythm, stronger, faster. Something within the aircraft structure was oscillating with increasing energy. Moments later, the situation escalated sharply. The vibration surged into violent shaking. A sudden structural failure may have occurred within one of the aircraft's critical components, possibly involving the tail assembly or control surfaces. When structural elements fail under aerodynamic stress, the aircraft can lose stability almost instantly. The smooth flow of air across the aircraft's surfaces becomes disrupted. Control inputs become less effective. The aircraft may begin to pitch or roll unpredictably. The pilots now faced a rapidly deteriorating situation. Attempts to stabilize the aircraft would have focused on reducing aerodynamic loads as quickly as possible. Power reductions, control inputs to counter unwanted motion. But at high speed and altitude, structural damage can propagate quickly. Once certain components fail, the forces acting on the remaining structure can become overwhelming. Investigators later concluded that the aircraft entered a catastrophic sequence of structural breakup. Sections of the aircraft may have separated under the intense aerodynamic forces generated during the oscillation. The aircraft's ability to remain controllable disappeared within seconds. To observers on the ground, the event unfolded quickly. The night sky above New South Wales was otherwise calm. Then debris began descending from the darkness. By the time the aircraft reached the ground, its structure had already been severely compromised by the forces acting upon it in flight. The impact occurred over rural terrain north of Sydney, bringing the flight to a sudden and tragic end. For the aviation community, the accident would soon raise urgent questions. How could a modern turboprop airliner suffer such a catastrophic failure during a routine flight? What mechanical or structural conditions had allowed the vibration to grow so rapidly? Could the crew have done anything differently once the oscillations began? Answering those questions would require an extensive investigation. Investigators would soon begin examining wreckage scattered across the countryside. Each fragment would become a clue, each damaged component a piece of the puzzle. And from those fragments, a clearer picture of the accident would slowly begin to emerge. Investigation and impact. In the hours following the disappearance of Flight 538 from radar and radio contact, uncertainty quickly spread through aviation authorities across southeastern Australia. Air traffic controllers responsible for monitoring aircraft movements along the airway between Sydney and Melbourne had initially expected a routine position report. Instead, silence followed. At first, such silence did not automatically signal disaster. Radio communication in the early 1960s could occasionally be disrupted by atmospheric interference or temporary equipment issues. Controllers attempted repeated contact. No response came. Soon afterward, reports began arriving from rural communities north of Sydney. Several residents described hearing unusual sounds overhead, followed by the distant noise of objects striking the ground. Within hours, authorities realized that a serious accident had occurred. The search and rescue operations began before dawn. Police units, local volunteers, and aviation officials moved toward the region where witnesses had reported falling debris. The search area lay across farmland and forested terrain within New South Wales. At first light, aircraft from nearby airfields joined the search effort. From above, the pattern of destruction quickly became clear. Debris from the aircraft had been scattered across a wide area, indicating that the aircraft had begun breaking apart before reaching the ground. This detail immediately shaped the direction of the investigation. Accidents involving aircraft breaking up in flight often point toward either severe structural failure or intense aerodynamic forces acting on the aircraft. Investigators now faced the difficult task of determining which scenario had occurred. The investigation begins. Responsibility for determining the cause of the accident fell to Australia's civil aviation authorities. Teams of investigators arrived at the site within hours. Their work would involve careful documentation of every identifiable component recovered from the wreckage field. Each fragment mattered: engine components, control surfaces, sections of the fuselage, pieces of the aircraft's tail structure. All were photographed, cataloged, and eventually transported for a closer examination. Because aircraft recorders were not widely installed at the time, investigators had no cockpit voice recordings or detailed flight data to analyze. Instead, they relied heavily on the physical evidence scattered across the landscape. The distribution of debris alone revealed important clues. If an aircraft impacted the ground intact, wreckage usually remains concentrated in a relatively small area. But when debris spreads across many kilometers, investigators know that structural failure likely occurred in the air. In the case of Flight 538, the debris field suggested exactly that. The aircraft had begun to disintegrate at altitude. Structural evidence. Engineers carefully examined the aircraft's major structural components. The wings of the Vickers Viscount were designed to withstand enormous aerodynamic loads. Under normal circumstances, they provided both lift and structural stability for the aircraft. But when investigators analyzed recovered sections of the wing and tail assemblies, they noticed patterns consistent with severe oscillation forces. Certain structural members appeared twisted or fractured in ways that suggested rapid aerodynamic vibration. This observation supported the possibility of aeroelastic flutter, the same dangerous phenomenon pilots are trained to avoid. Flutter occurs when aerodynamic forces cause a control surface, such as an elevator or rudder, to oscillate uncontrollably. If the oscillation grows strong enough, it can tear apart structural components within seconds. Modern aircraft incorporate numerous design safeguards to prevent such conditions. But in the early generations of turboprop aircraft, engineers were still learning how subtle structural characteristics could interact with aerodynamic forces. Mechanical analysis. Attention also turned to the aircraft's engines and propeller systems. The Rolls-Royce Dart turboprop engines powering the Viscount had accumulated an impressive safety record across the global airline industry. Investigators therefore examined the engines carefully to determine whether any malfunction might have triggered the vibration noticed during the flight. Recovered engine components showed evidence of operating normally at the moment of breakup. This finding suggested that the engines themselves were unlikely to have caused the catastrophic oscillations. However, propeller systems remain an area of interest. Even a small imbalance in a high-speed propeller can generate powerful vibrations that travel through the aircraft's structure. Maintenance records were therefore reviewed in detail. Investigators searched for any previous reports of unusual vibration, component replacement, or maintenance irregularities involving the aircraft. Maintenance records. Airline maintenance documentation often provides a detailed history of an aircraft's operational life. Technicians log routine inspections, repairs, and replacement of worn components. Investigators examine these records carefully. They look for patterns. Had the aircraft experienced recurring vibration issues? Had any structural components been recently repaired? Was there any indication that a critical component might have been weakened over time? Maintenance crews who worked on the aircraft were also interviewed. These technicians described their inspection procedures and any irregularities they had encountered during recent servicing. At this stage of the investigation, every possibility remained open. The accident might have involved an unexpected structural weakness, a mechanical failure, or a complex interaction between aerodynamic forces and the aircraft's design. Broader implications. As the investigation progressed, aviation authorities recognized that the outcome would carry implications far beyond a single flight. The Vickers Viscount fleet was operating worldwide. Hundreds of aircraft of the same type continued flying daily passenger routes across multiple continents. If a design vulnerability existed, identifying it quickly would become essential. Engineers therefore worked closely with the aircraft manufacturer to review structural design calculations, flight test data, and operational history. Wind tunnel experiments and structural analysis helped determine whether certain aerodynamic conditions might produce dangerous oscillations under rare circumstances. The aviation industry had learned through previous accidents that complex systems sometimes reveal weaknesses only after thousands of hours of operation. Each new investigation therefore contributed to a broader understanding of aircraft safety. Public reaction. News of the accident spread quickly through Australia. For passengers who regularly travel between Sydney and Melbourne, the event was deeply unsettling. The route had long been considered routine. Air travel, while still relatively new to many people, had developed a reputation for reliability. Airlines responded by reviewing their operational procedures and cooperating fully with investigators. Passengers continued flying, but the accident had introduced a moment of reflection within the aviation community. Even well-established aircraft types could encounter unforeseen problems. Understanding those problems required patience, technical expertise, and careful analysis. In the months that followed, investigators continued assembling the pieces of the puzzle: engineering reports, structural analysis, operational records. Gradually, a clearer picture of the accident began to emerge. And with that understanding came an important question. What lessons could aviation learn from the loss of Flight 538? Because in aviation, every investigation carries the same purpose, not only to understand the past, but to protect the future. Safety legacy. In aviation, the conclusion of an accident investigation is never simply the end of the story. It is the beginning of a long process of change. Each investigation adds to a body of knowledge built over decades, knowledge written not in theory, but in experience. Aircraft designs evolve, maintenance procedures adapt, regulations expand. The loss of Flight 538 became part of that ongoing process. Investigators had examined every available fragment of the aircraft. Engineers had analyzed structural stresses and aerodynamic forces. Airline procedures had been reviewed and maintenance histories studied in detail. Gradually, the picture that emerged was not one of a single dramatic failure, but of complex interactions within a sophisticated machine. The Vickers Viscount, like many aircraft of its era, represented an important stage in the evolution of commercial aviation. Turboprop airliners had introduced new performance capabilities, allowing airlines to operate faster and more efficiently across medium-distance routes. Yet these aircraft also revealed challenges that engineers were still learning to fully understand. Among the most significant was a phenomenon of structural vibration and aeroelastic flutter. Flutter is not caused by pilot error, nor is it usually the result of obvious mechanical failure. Instead, it emerges from a delicate interaction between airflow, structural flexibility, and mechanical components. When those elements align in certain ways, oscillations can begin. If those oscillations grow beyond the structure's tolerance limits, the consequences can escalate rapidly. For engineers in the early decades of turboprop aviation, understanding and preventing flutter became a major focus of research. The investigation into Flight 538 contributed valuable information to that effort. By examining the structural damage patterns within the wreckage, investigators were able to better understand how oscillations might develop within aircraft structures under certain conditions. The findings helped refine inspection procedures for control surfaces and structural attachment points. Airlines operating fleets of the Vickers Viscount and other turboprop aircraft began implementing more detailed maintenance inspections aimed specifically at detecting early signs of structural fatigue or vibration-related stress. Aircraft manufacturers also use such findings to refine future designs. Engineers strengthened certain structural areas, and improved analytical models used to predict how aerodynamic forces interact with flexible aircraft components. These improvements gradually reduced the likelihood of uncontrolled structural oscillations in later generations of aircraft. Another long-term outcome involved the evolution of flight monitoring systems. At the time Flight 538 occurred, many aircraft did not carry modern flight data recorders. Investigators therefore relied heavily on physical wreckage and maintenance documentation to reconstruct events. In later years, aviation authorities around the world expanded requirements for onboard recording equipment. Flight data recorders began capturing detailed technical information about aircraft performance, including control movements, engine parameters, and flight attitudes. Cockpit voice recorders preserve conversations and operational decision-making within the cockpit. Together, these systems transformed accident investigation. Instead of relying solely on physical evidence, investigators could now reconstruct events with remarkable precision. Each accident became an opportunity to learn in far greater detail than before. Operational training also continued evolving. Pilots flying turboprop and jet aircraft received increasing instruction about aerodynamic vibration and structural stress conditions. Although flutter events remain extremely rare, crews are trained to recognize unusual vibration quickly and respond by reducing speed and aerodynamic loads whenever possible. Modern aircraft incorporate numerous safeguards designed to prevent these conditions from developing in the first place. Computer modeling, structural reinforcement, and extensive flight testing all help ensure that aerodynamic oscillations remain safely within control limits. The industry's understanding of these phenomena has grown steadily over time. Beyond the technical lessons, the accident also carried a broader reminder for the aviation community. Even during periods of technological optimism, aircraft remain complex machines operating within an equally complex environment. Safety depends not on perfection, but on constant learning. Every irregular vibration, every unusual mechanical behavior, every unexpected system interaction becomes a data point in the industry's ongoing effort to reduce risk. Airlines, engineers, regulators, and pilots all contribute to that effort. The process never truly ends. Today, aircraft traveling between Sydney and Melbourne complete the journey in less than 90 minutes. Modern jetliners cross the same air corridor guided by satellite navigation, monitored by advanced flight computers, and protected by layers of automated safety systems unimaginable in the early 1960s. The route remains one of the busiest in Australia. Passengers board aircraft much as they did decades ago, carrying luggage, checking tickets, settling into their seats. The journey feels routine, ordinary, and that quiet routine is itself the result of decades of investigation, engineering refinement, and operational improvement. Behind every safe flight lies a long history of lessons learned. Some of those lessons emerge from difficult moments in aviation's past. The story of Flight 538 is one of those moments. It stands not only as a reminder of the risks that once existed within early generations of airliners, but also as part of the process that gradually made aviation safer. Aircraft today are stronger. Monitoring systems are more sophisticated. Investigations are more precise. And every improvement traces its origins to careful study of events like this one. As the years passed, the accident slowly moved from headline news into the archives of aviation history. Yet its lessons remain embedded within the design of modern aircraft and procedures followed by pilots and engineers every day. Flights still depart from Sydney, climbing into the evening sky before turning south toward Melbourne. Engines settle into steady rhythm. Navigation lights blink quietly against the darkness. Passengers read, sleep, or watch the distant coastline pass beneath the wings. For them, the journey is uneventful, routine, and in aviation, routine is the ultimate measure of success.